Welcome to part 2 of our first concave mirror problem. In part 1, in a separate video, I showed you how to draw a ray diagram that will allow you to locate the image formed by a concave mirror with an object in front of it. And that's the diagram that we have here. Now in my template on page S28, I've got a little bit of space below each diagram template so that you can do the math work there, because what I'm going to show you now is how to use two equations that basically are shortcuts for doing what we did in the diagram. We're still going to be able to locate the object, figure out whether it's upright or inverted, real or virtual, smaller or larger, and all of those things, but it's a bit more mysterious when you just use a math equation. I am not going to attempt to derive this equation for you. In other words, to show you why it works. That's actually a fair amount of geometry that I don't know is pertinent right here. But as long as you have a diagram to go along and accompany your math, then I think you'll be able to see that both of them work pretty much equally well. Most of the problems I do with you, I'll have you do both. So we're going to start by looking at page S27, which has two equations down at the bottom. I'll show you here. The one I call the mirror lens equation because it's actually used not only for curved mirrors but curved and spherical lenses as well. We'll see that in another unit. And what it does is it relates the three important quantities that you might want to know in a problem such as this. One is called the focal length of the mirror, and the focal length we saw in the diagram is the distance from the center of the mirror to the focal point. So in this case here, we've got 5 units, 5 centimeters we'll call them, in between there. So I'm just going to write this down on the page so we know that that is an important property of this particular mirror. And then back on the equation here, the other quantity that we're going to relate, or the two really, are the distances to the object and to the image. Okay, so in a typical problem in here, I'll give you the location of the object and ask you to find the location of the image. So in our situation here, if you look at where we put the object, this is that arrow object, and you count out here, there's 5 centimeters to get to the focal point, 10 centimeters gets you to the center of curvature, and then 5 more units gets you out to the object. So that means the distance to the object is 15 centimeters. I'm not worrying too much about significant figures. You notice I put decimal places on each of these just because I've got little grid lines out to the centimeter, so I can pretty much estimate that they're right on the line. That's why I'm putting the 0.0. Now, if we want to find the distance to the image, then we're going to use this relationship here. This is one of the important ones that's also on your reference page. But what I did is I did a little bit of algebra for you and put it in a form over here on page 27 that I think is just a little more useful. It's already algebrated for the image distance. And I have, instead of 1 over f and 1 over do, I have it written in a form that's more convenient for most of your calculators. The inverse of f minus the inverse of the distance to the object. Okay. Now when you subtract those things, that'll give you the inverse of the distance to the image. So that's why I have this additional inverse step here. And I'll show you on the calculator what this looks like when we punch it in. So I already wrote down the two values that we have here. And so now I'm going to do this McManus style, which is to always write the symbols first. And so the inverse of the focal length minus the inverse of the distance to the object. All that subtracted and then inverted again. And then we'll put in the numbers. The inverse of 5. Now I'm leaving the units off of this just for clarity. But as long as all my units are identical, I know that my distances will come out with identical units. Okay. So the inverse of 5 minus the inverse of 15, and then all that inverted. So here's how I'm going to put this on my display. Hopefully this shows up pretty well. Let me maybe change the contrast just a little bit here. Here we go. So if you do this in parentheses, the inverse of 5 minus the inverse of 15, and then close the parentheses and hit the inverse key again. And it gives you a 7.5. Now, don't just blindly trust your calculator. A couple of things you want to think about here. First, since we've already done the diagram, ask, was it reasonably close to what the ray diagram showed me? And when you look at where our image distance ended up, we always measure along this principal axis, this dashed line here. We're almost spot on because mine is just about 7.5 centimeters from the center of the mirror. All distances in a mirror problem are measured from the very center of the mirror right along the principal axis. The other thing to consider is what we call sign conventions. So at the top of page 27, I'll show you some sign conventions. For our mirrors, we're dealing with a concave mirror, so we used a positive number on our focal length. That was our positive 5. And if we come out with an image distance that's positive, that means that it will be a real image. Okay? And in this case, we already knew it was a real image from our diagram because the light rays that reflected off of the mirror really did intersect somewhere. They didn't just virtually intersect the way they do for a plane mirror and some other mirrors. So we knew this had to be real, and real images will always have positive image distances. So those are a couple checks that you can do. So that tells us two things. With this number, we know exactly where the image is located. We could tell from the diagram it was between the center of curvature and the focal point on the principal axis, but we didn't know exactly where. Now we know, in this case, it's exactly halfway in between them. And we can tell that it's real. Okay, now we're going to do the other equation. This is what I call the magnification equation. And again, I wrote it in two forms. It's actually a proportion. There's something we call the magnification of a particular object and image, and that just tells you how much shorter or taller the image is than the object started out. And here's, if I cover up the M here, it tells you that the height of the image is to the height of the object as the distance to the image is to the distance to the object. And there's a negative sign in there that I'll point out what that means in just a minute. So your heights are directly proportional to how far each thing is from the mirror. And we can kind of look here back at our diagram, and we can see that because the object was farther away from the mirror than the image was, it also ended up that much taller. So we're going to figure out just how tall this image should be by using the magnification equation. So back on page 27, I'm showing it here algebrated for the height of the image, which is what we're looking for here. And so I'll write in the form that we need to use it. The image height is the negative of the object's height times this ratio di to do. Now we just calculated di, that's why we had to do that first. And now I'll take a measurement of the object's height. Now I have to go back here to my figure. 1, 2, 3, 4, 5, 6, 7. 7 squares tall is how tall the object is. So I'll call that 7. Again, I'm going to keep all my units in these little grid units, which are centimeters. They're not actually going to measure a centimeter on your paper. I'm just calling them centimeters. And then the image height, or the image distance rather, we found is 7.5. And we had already determined the object's distance from the mirror to be 15.0. Okay, now if we grab a calculator, actually in this case I'm not going to use my calculator because I can tell that inside these parentheses here I have a ratio of 1 over 2 or a half. And so a half of 7, don't forget the negative sign thrown in there, is 3.5. I'll put my units on now that I'm finished with my final answer. Then I'm going to give it a couple of checks like I did before. For example, does my image height that I calculated with the equation match fairly closely with what I drew? Now it's not going to be perfectly matched, but if you look at the image here, we have about 1, 2, 3, and a little more, so roughly 3.5 squares. And what do you make of the negative sign? I think if you look at the image here in the diagram, it kind of makes sense that you might have a negative, but I have it on page 27 if you want to see it. What does a negative image height mean? It means it is an inverted image. Okay, and I put in parentheses here real. That's because when you have a reflection off of a mirror like this, any inverted image will also be real. Okay, that's a good rule of thumb. So all of those kind of check out. And so as you can see, my list of the 4 values here that the 4 descriptions of this image, I got that by just doing the ray diagram, but now I've reinforced all of these. I can see that it's inverted just by looking at the sign of the image height. I can also tell that a negative image height is real. I know that also because I have a positive image distance, my positive 7.5. Smaller, I could tell smaller, but I can also tell that it's smaller because my magnification in this case is 1/2. The number here in parentheses, di over do, tells you the magnification of this. In this case, maybe you call it demagnification, but I don't generally use that term. We just say a magnification of 1/2. And then the location, we could already tell from our calculation of the image distance, 7.5 is located between the center of the mirror and the focal point of this mirror. So we've got all of the values that we need here, and they match pretty well with the diagram. So now we've seen really both different ways to solve these mirror problems, and if you can just get comfortable with the different kinds of scenarios, then I think you can handle any curved mirror problem that I'll ever give you. So we'll go over this more and apply it somewhat in class if you have any questions. We'll see you in the classroom.